Hi, everyone. Thank you so much for inviting me. It's really a pleasure to be here. I'm curious to see so many interesting speakers. So let me introduce myself. I am a research scientist in the Max Planck Institute for Human Development, as Ophelia was saying, in Berlin, where I lead the hybrid collective intelligence team at the Center for Humans and Machines. So today I will tell you a little bit about two experiments that I did in the past years that show how human and algorithmic biases tend to interact sometimes, which in turn can affect the performance of hybrid groups, which are groups that are composed of humans and machines. So in the last decade, we have seen, growing concerns that the digital environment where we spend our lives may shape the information and diversity of opinions that we are exposed to, and so the perception of reality that can stems from it. So filtering algorithms, for example, search engines, ranking systems, news recommender systems, were created, with the goal to help people find what they liked in a massive landscape of information. Unfortunately, decades of research in social psychology tell us that what people like sometimes can not be good for them. So, for example, in this paper that I wrote with Nick Young, I show that people seem to value agreements with other people and with the information that they consume over and beyond the accuracy that that information carries. Because somehow disagreements and uncertainty are psychologically, very costly. So, what's wrong with finding information and people that tend to agree with you? Well, even if at the individual level, this might not, might feel it's not a big deal. There might be problems at the population level when information across different people is aggregated together, like, for example, in democratic processes. Elections, or simply when we engage in social learning, because there is a risk that reducing the diversity of information and the opinions in a group can distort our collective perception of reality and makes us victims of making correlated mistakes. So herding, groupthink, this sort of things. However, these hypotheses were never tested in the lab because they're very difficult to test. And so in this first experiment that I'm going to present today, which was recently accepted in Nature Communications, I manipulated the trait diversity of different groups and asked them under very high time pressure to search for information and news online to make a forecasting judgment about future events. So how I did this? So I asked volunteers on MTurk a large battery of questions. These were dimensions that are often used by recommendation systems online to segment users. For example, different demographics, political orientation, but also some relational and network indicators, right? So, for example, I asked them about the political orientation of their average friend, as well as some personality traits that we needed for assessing, for example, their need for cognition, or the famous cognitive reflection test to assess understanding of sort of system 1, system 2 thinking. And then I took this distribution of people along these many questions, and I segmented them into 3 chunks using very standard clustering algorithm. And you can see the three chunks here in the figure, named as core, inner, and outer segments. And what I did was take the people in the core segments, which means that they gave responses that were very close to the mean of the population. And I randomly assigned them to interact with people that were that gave similar responses to their own or more different responses. So a second dimension that was manipulated during the study was the group modularity. So when modularity was low, people interacted in one large group. So think about it as it could be like a Reddit forum. But when modularity was high, people interacted in many small groups that were kind of insulated from each other. So think about many small WhatsApp groups. And then I asked them to predict future geopolitical events, such as elections or political unrest in foreign countries. And importantly, all these problems were unknown at the time that the experiment was run. So 3 days after this initial questionnaire, participants made an individual prediction before and after they could gather information and news online on their browsers. And then they discussed all this information that they had collectively gathered in these like small groups they were assigned to, and could update their initial forecasts, as well as they were asked to make a joint forecast as a group. So 6 months later, we knew about which predictions were right, which predictions were wrong, and we could calculate the performance of our participants and of our groups. So what did I find? So first of all, when working together, people were more effective at predicting the future, right, than they were in isolation. So for example, here on the y-axis, you can see the forecasting error that was made when I aggregated these forecasts together. And you can see that the consensus forecast had a lower error than the initial forecasts. So this seems to be good news. But I also found that search engines seem to feed similar news to similar people. When you look at the forecasts that were made before online search engines were used by the participants, so here on the left-hand side of the slide, more similar people, that is like people who gave similar responses during our initial survey, did not correlate in their forecasts. So this can be seen by on the left-hand side, the relationship between forecast correlation and the similarity between two people in our population was quite flat. But after they gathered information online, their forecasts became positively correlated, the more similar they were. So, and this, you can see it on the right as this like positive correlation that emerges between the two axes. So the algorithm that they use to gather information somehow seemed to like skew the diversity of information that people could find online and bring back to the group. Now the question is, did this affect the ability of the group to predict the future? Did they impact their accuracy? And so it did. The groups who were assigned to this high composite diversity condition tended to perform better than those that were assigned to the low composite diversity condition. Again, here I'm plotting the forecasting error on the y-axis. So lower values indicate better performance. And this is likely because larger and more diverse groups, again, with a caveat of our specific composite diversity measure, could find more and more diverse information online than more, say, homogeneous groups. But One interesting finding was that when forecasts were made and were aggregated across many small insulated groups, which is in our modular condition, this seemed to alleviate some of the problems that we found in the low composite diversity groups. Because somehow these small groups could not communicate among each other and thus could not make correlated errors. So essentially errors that were made in one group could not spill over to the others. And so when I went and aggregated these forecasts together, this improved accuracy. And this was a nice replication of a paper by Navajas and colleagues that we also replicated here. So to summarize this experiment, it looks like search engines somehow the search engines that people commonly use to search for relevant information, news, seem to feed similar information to similar people. And this, in turn, kind of negatively affected the performance that a large population of people could achieve, and the accuracy of the representation of the world that they could form. At the same time, splitting large groups into modular ones, might be hopefully like a possible intervention to avoid the risk of herding. Okay, so I want to move on to the second experiment that I will present today, because it tackles a perhaps more interesting, but I guess complementary question, which is, can the interaction of human and machine biases that we saw in the previous experiments be used to our advantage to sort of improve people's performance? I cannot see the crowd, the people and the audience, unfortunately, but who knows what this picture represents? So
playing AlphaGo, right?
Right. So this is the first time that an algorithm, AlphaGo, in this case, as correctly identified by Ophelia, beat a human player at the game of Go. And this, in particular, in this frame, is the reaction of Go champion Lee Sedol to this now famous AlphaGo move 37, which was the most surprising move that AlphaGo made, before beating the human champion. And AlphaGo itself calculated the chances of a human player making the same move as 1 in 10,000. So it was a very innovative move that led the machine to this kind of historical victory. And AlphaGo was able to make this move because it was not trained on human data like many other algorithms, but it was trained by playing the game against itself. So essentially, AlphaGo could learn how to act in this problem space without being biased by how a human would play. And so this, for us, opened up the fascinating question, can we learn innovation from machines? And what are the limits of this hybrid social learning? So this is the work that a student in my group, Levin Brinkman, did or is doing for his PhD. And we are about to submit to Philosophical Transaction of Royal Society A. And this is what Levin did. So many decisions, including games like Go and chess, can be characterized as a sequence of states and transitions between these states. So with each action determining transition between states being associated with a reward or a loss. And so planning becomes very important if you want to maximize your long-term rewards. So for example, the last time you took a flight a long time ago, you probably had to plan your routes, and you took into account maybe information about the cost of the tickets, hours of flight, and so on. So Levin used this task by Quentin Huis and Peter Dayan, where people have to hop between nodes on a network to maximize their rewards over the course of a number of steps. So for example, here, imagine you are in Jonesville on the top left. This is a picture from leaders and colleagues. Imagine you are in Jonesville at the top left, and your task is to plan 8 moves, so to collect as many points as possible. And the points are shown in green, are the little number in green. And at the same time, you want to minimize your losses, which are like the numbers in red. So what actions would you choose? I'll give you a moment to think about it. Okay, so the correct answer is to make a loop that goes from Jonesville to Williamsville, to Bakersville, to Smithsville, and back to Jonesville. Now, we know from past research that people tend to have what we call a loss-subversive pruning bias, which means that they stop exploring options after they encounter an initial loss, even if this is actually associated with larger rewards in the very long term. So, for example, in this case, once you get to Williamsville, it is difficult for people to consider jumping on Bakersville because this is associated with a larger cost than, for example, jumping to Brownsville. So Levin readapted this task and placed it in a transmission chain paradigm, which is a paradigm that is often used to study social learning, cultural evolution, innovation spread, and so on. And people in our experiment could replay the sequence of actions that the previous participant had chosen before they were asked to play the task themselves. And so in this way, when a good solution was discovered by one of the players, this could be imitated by the next one. And so we can assess how good solution spread from one generation to the next one. So this is an example of our control condition where 8 people are put in a transmission chain, one after the other. And you can see that the last person in the chain accrues a better score than the first one. And this is because people can benefit from what came before them. But Levin also created a hybrid chain where in the second generation, he replaced a human player with a machine player. And importantly, however, the machine was designed to show the opposite bias than humans, which means that the machine was more likely than human to explore decisions that followed a large loss. And the hypothesis was that by mixing together humans and machine with different biases and different decision strategies, this hybrid chain would do better than a chain composed of only humans, especially in those environments like the one that I was describing earlier, where humans seem to have a systematic suboptimal bias. So what did we find? First, we found an increase in the performance over the generations. And this is shown by this upper trajectory on the graph, suggesting that people were indeed benefiting from seeing the previous player answers. So on the y-axis here, you can see the performance improvement. And on the x-axis, you can see the 8 generations of a chain. The colors represent 2 different environments that we tested. One was called human rewarding, where actually human biases was adaptive to find the right solution. And one other environment, which is more interesting and corresponds to the examples I gave you earlier, called human regretful, where the human bias was actually maladaptive. And so this was the environment where we expected the machine could really show people the correct answer. So what was the effect of adding a machine to a transmission chain? So here I plot the difference in performance between the human only and the hybrid chain. So our treatment and control condition for these two types of environments. And you can see that there is, this spike in generation 2 when the machine player was introduced. And this suggests that, indeed, the machine player that we added was more likely than a human to find a good solution in that specific type of environment. However, you can also see that the machine solution is quickly lost over the generations. So, for example, we find a significant difference between the orange and the blue line in generation 2 and 3, but not in the following generations. So somehow people lost what they had learned from the machine. So why did the machine, objectively better solution did not stick? So in the paper, we focus on two possible explanations. The less optimistic one is content bias, which means that certain features of the solution simply do not stick. So for example, people might simply be resistant to copy something that goes against their inner bias. Of course, not necessarily consciously, but they might. And the more optimistic explanation is that maybe one machine was just not enough. And being exposed to the algorithmic model multiple times is a necessary condition for hybrid social learning to occur. So to test this last hypothesis, we built a simple agent-based model where we manipulated the pruning and the copy bias of each agent so that we could model the behavior of people and machines. And we let agents learn from each other, like in our experiment. And the plot shows the rewards that the chain achieves over the different generations. So at the top, you see the orange lines. These are machine-only chains. And at the bottom, the blue lines, these are human-only chains. So in this type of environments, you see that the machines clearly outperforms the humans. Now, the green lines show the hybrid chain with only one machine among the many humans that sort of it's like in our behavioral data. And you can see that the pattern of results is the same, right? So the spike and then a decay, which shows that the machine benefits kind of are lost over time. However, when you add a condition where, this was not in our experiment, it was only in the simulation, but when you randomly shuffle sort of humans and machines, like perhaps in modern sort of hybrid ecologies, you can see that the red line now is in between and sort of outperforms both the human only, but also the hybrid chains with a single machine. So this suggests that perhaps the limits of hybrid social learning in these types of environments is just repetition, right? So being exposed multiple times to good solutions. So this is my second to last slide, and this is perhaps a take-home message that I hope you get from this talk, which is, I think it should be this one. So the human and machines both show different biases, either by evolution, learning, or design. And these biases can interact together in hybrid environments that we face every day. But this interaction must be taken into account when we design our digital ecosystem, because perhaps we don't feel that it affects us as an individual, but it definitely affects us as a group. So this is my last and most important slide. I have talked about many ideas in this talk. None of them would have been possible if it wasn't for these incredible people that I had the fortune to find on my path. Thank you so much for listening, and I'm looking forward to your questions.
Thank you so much, Niccolò. There are quite a few questions, and actually we have two clarification questions from Antonia Hamilton. So one, the confirmation was for the machine imitation study that you presented. Participants were told that the machine was giving the solution. Or...
No, it was completely...
Okay.
We just replayed the action, so they couldn't know if it was a machine or a human. Actually, we didn't even say that there was the possibility of a machine playing. Okay,
great. And then Antonia also was asking whether in this time the first study, the difference in the search is in the search engine itself, or in which items people choose to read from the list of 10 results?
Sorry, could you repeat?
Is the difference that people were getting from the search engine itself, or what people were choosing to read from the list of the 10 results?
In this task, we just gave the problem to solve. So, for example, what is the likelihood that there's going to be like X amount of deaths in a Houthi rebel attack by this date? So very precise questions. And we said you have the opportunity to browse the web, search for relevant information, but we didn't give any other sort of targeted advice. So they could use Google, Bing, whatever they wanted, but they had a very limited amount of time. So the time pressure was the most important.
Maybe then in the case they were phrasing the question also in the same way. That's right. I think we have time for one last question. So Jurgis, this is a big one. Jurgis was asking why you think there is a difference in the performance between modular and non-modular groups when it comes to bias predictions.
Why there is a difference between modular and non-modular?
Yeah.
So this is actually, the second axis, this modularity, was inspired by a paper in Nature of Human Behavior that came out a few years earlier by Navajas and others and colleagues, where they actually asked either like a large crowd or like the crowd was divided into these like modular groups. And there is a benefit of modularity because people can benefit from social learning, from sort of discussing the ideas and trading uncertainty within very small groups. But if they make a mistake, that mistake doesn't sort of spill over to new groups. So in a way, you maintain independence, which is super important in forecasting and aggregation, but at the same time, you benefit from others.